The Space Shuttle Challenger in 1986 blew up about a minute after it took off from the Cape. And over the next few years, there were a series of accident investigation reports that came out and engineering assessments of what had gone wrong in that accident. There's a long history of what went on there. But here's a quote out of a 1989 OTA assessment that looked at warnings of a possible new shuttle accident. So that basically said, look, if the shuttle reliability is presumed to be about 98%, there's a 50-50 chance we'll lose another one within 34 flights. The probability of maintaining the orders declines to less than 50% after flight 113. So this wasn't a prediction about the Challenger disaster. It had already happened. This was 3 years later. What they were predicting was if we fly another 34 flights, the chances are 50-50 that we're going to have another disaster on the Space Shuttle program, even at 98% reliability. And 98% is considered quite good back in the 80s. Today it's not, but back then it was considered excellent. So what happened to that estimate? On January 16, 2003, Space Shuttle Columbia took off from the Cape. And as normally happened on that day, we have a lot of high-speed cameras running, filming it. The spray foam insulation that covers the rocket boosters and the tank typically break off and we get a raining down of that. But there was a particular piece of foam debris that came off of the large tank, and it was photographed like this on January 16th. So everyone knew it was there. It was fairly routine to look at the shuttle and decide whether the pieces of debris presented any kind of risk or not. So the problem wasn't that foam debris came off the tank. Is that the piece looks a little larger than what they normally would have expected, so they've got to assess the basic risk. So the Space Shuttle Columbia was now on orbit going around the Earth, and engineers at NASA now had to figure out if we had a problem. 2 weeks later, Space Shuttle Columbia came back in on its re-entry, and this is what Americans saw. It broke up on re-entry over Texas and scattered debris of the Columbia disaster across 3 states, killing everyone on board. So by 2003, the Columbia Accident Investigation Report came out, and you've got that among the handouts in this class. So here we were again, a few years later, looking at another Columbia disaster. So what started at the Challenger disaster in 86 with that statistic that I showed you coming out by 89. Now here it was 2003. It was time to look again at what had happened and what went wrong in the Columbia disaster. And could engineers have done anything about it? These are actual quotes out of that report. On page 191, we have this section that talks about engineering by viewgrass. So what the report observed was that as information gets passed up the organizational hierarchy, talking about NASA, but I would suggest it applies to virtually any engineering organization. As it goes up the hierarchy from people who do analysis to mid-level managers to high-level leadership, key explanations and supporting information is filtered out. Now, in this context, it's easy to understand how senior management might read a PowerPoint slide and not realize that it addresses a life-threatening situation. Here's the actual example of a PowerPoint slide from that report. So it's an actual PowerPoint slide that was used in a debris assessment briefing at NASA at the time of the Columbia disaster. So Columbia was on orbit, and the engineers were challenged to figure out what the risk was and then present that data to the management team. The highlighting in this slide and the arrows coming in from the right are highlighting prepared in the actual Columbia disaster report. It wasn't present in the original slide used in the briefing. But if you just review what goes on here, you'll see how often engineers can present data up the chain of command to management that actually loses most of its meaning. Notice this isn't an engineering diagram. It's not an engineering model. It's engineers boiling down some findings into a PowerPoint slide that they think management can understand. And it basically says they looked at the spray-on foam insulation, that's the SOFI acronym, and looked at the tile test. Using a piece of software called Crater. Crater was a simulation model that they had designed at NASA for estimating the potential risk and impact of spray-on foam insulation hitting the top side of the wing of the Challenger, Columbia. That was the disaster they were looking at. Did this piece of spray foam actually damage the Columbia vessel enough that the people up in orbit were in trouble? We now know in hindsight they were doomed, but that wasn't known the day this briefing was given. So let's take a look at what it says. It says the Crater overpredicted penetration of tile coating significantly. If you can figure out what that means, you're smarter than me because I'm not sure what it means. But basically, they're saying that their model over predicts penetration. So I guess that means that there's some penetration being predicted by the model that they felt was being overestimated by the model. So in terms of initial penetration described by a normal velocity, whatever that means, that it varies by the vast volume of the projectile. 200 feet per second for a 3 cubic inch block. So something about at 200 feet per second, if the little piece of foam is 3 cubic inches, I guess that's a threshold potentially that the crater uses for knowing if there will be damage. It also says significant energy is required for the softer particles to penetrate the relatively hard tile coating. How much? What kind of energy would be significant? Was there enough in this case? It says conversely, once the tile is penetrated, you'll get significant damage, and that's true. The front end of the wing, if there was any penetration at all, considering the forces and velocities involved in a space shuttle reentry, that would be bad. So it said minor variations in the total energy above the penetration level can cause significant tile damage. So what does that mean? If you were a manager reading these slides, what do you think the engineers are trying to tell you? The last bullet is fairly important. Flight condition is significantly outside the test database. What does that mean? Basically, what the engineers on the last bullet are saying was, for all we've just told you about our use of the crater model to make a prediction, it turns out the crater model is useless because our estimate of the size of that piece of spray foam is 1,920 cubic inches. And our software simulation is designed to handle pieces up to 3 cubic inches. So 1,920 cubic inches is so far out of the realm of the test database that we don't really know what's going on. So management didn't know what to do with this. Management didn't do anything with it. They basically moved on. But this is engineers communicating to management. You don't need to know the model, but here's an example of the crater model trying to make some predictions about the probability of penetration as things go through. So, I've circled here the asterisks. Notice that several of the key parameters for this particular flight were outside the experimental test limits. So the model can handle up to 3 cubic inches. When this slide was put together, they thought it was at 1,200 cubic inches. It turned out to be 1,920. It can handle a piece of foam up to 1 inch long. It turns out this piece was about 20 inches long. And in terms of dimensions, 3 inches by 1 inch, so 3 cubic inches. The estimate at the time was that this block was 6 by 10 by 20. And the projectile shape should be a cylinder with round edges. This turned out to be a block with square edges, which produces a lot more force when it hits on the corner of a block. So again, this small rod up in the upper left here, this is the type of projectile that the crater model was designed to make estimates for. So had it been that size, crater is a good model for predicting the potential damage to the wing. The 20-inch cylinder under it is the model that they believed they were dealing with at the time they made their presentation to management, the 20-inch cylinder. The block to the right turns out to be what the shape actually was of the piece that came off, 20 by 10 by 6 cube. So clearly the model they were working with to make their decisions was wholly inadequate for making any kind of assessment of exactly how much debris or damage they could expect to the wing on re-entry when Columbia came down. So again, going back to the report, at many points during its investigation, the board was surprised to receive similar presentation slides from NASA officials in place of technical reports. So not only was a PowerPoint slide used to brief management during the episode, but even in analyzing the episode after the fact, engineers and NASA officials tended to bring in PowerPoint slides again rather than technical reports. So the investigation board, in their conclusions, said the board views the endemic use of PowerPoint briefing slides instead of technical papers as an illustration of the problematic methods of technical communication at NASA. And again, I would argue not NASA. Everywhere I've worked, this has been a problem. Engineers do their jobs, engineers work with their models, engineers develop their designs, but they don't tend to share them up the chain of command to management. Instead, they create PowerPoint slides that are more or less useless in actually communicating what's going on. So it's not surprising that management ends up not understanding the risks that are involved, and engineers end up frustrated that management doesn't seem to understand what's going on. So again, back to that assessment in the 1989 Challenger disaster report. It basically said that within 34 flights at 98% reliability, we're going to have a 50-50 chance of losing an orbiter. It turns out the Columbia disaster was the 34th flight after Challenger. The 113th flight of the space shuttle was the Columbia disaster when that went up. So we're learning a lot about the binomial distribution, and basically that applies here because whether your flight is successful or not is a two-part state. So the question is, how long can you go on and continue flying missions before you're going to get into trouble? So our binomial distribution here says in the next 34 missions with a probability of 0.98, what's the probability of only having 33 flights successful? So will the 34th flight fail? And it turns out that there was a 35% chance that the 33rd flight would fail, and a 49.6% chance that any of the next 33 flights would fail. So the 34th flight actually failed. At that point, they had better than a 50-50 chance going in because they surpassed the 49.6 when they went to the 34th flight. So again, there was a 50-50 probability of succeeding, and they in fact failed on the 34th flight. Notice how flat the distribution curves are to the left here. They're virtually zero. Had there been only 10 more flights or even 20 more flights after the Challenger, we would not have had a problem with Columbia. The space shuttle program simply wasn't designed to fly for as many years as it was supposed to fly. So again, if we'd only had 10 or 20 more flights, what this curve shows is 98% reliability would have gotten us through there with no disasters. But even at 98% reliability, you eventually are going to have a failure if you push your system too far. And when the space shuttle was designed back in the 70s and 80s, it was really only designed to fly probably no more than 100 times. The goal had been to retire the space shuttle around the turn of the century. What tended to happen is other mission critical applications, particularly the space station that's now circling the Earth, didn't get built on time, and they needed the shuttle to get it onto orbit. So every time they started to cancel the space shuttle program to get it off the schedule, politicians typically got involved, and citizens started to complain, oh, we're going to lose jobs in the Cape, and oh, we have to have the national pride of keeping the program going. And politicians kept extending the program. So even though it was only designed after Challenger to go another 10 or 20 flights, it ended up going 34 flights. We never should have been flying it that long. Engineers knew we shouldn't be flying it that long. This probability right here was in the Challenger accident report in 1989. In 1989, we predicted that if we fly 34 more times, we have a 50-50 chance of losing another shuttle. And that's exactly what happened as we went through. So engineers should have stopped it. Engineers after the Challenger disaster who knew there was a problem and couldn't stop the flight, even though they talked to management and said there's a pretty good chance the Challenger is going to blow up. In fact, some engineers actually said that morning, the Challenger will probably blow up about 1.5 to 2 minutes after it takes off. And it blew up at 71 seconds after liftoff. And those engineers struggled a lot with what could they have done to stop that mission. Management wasn't listening. In this case, we have the data. We know that if we were going to fly the shuttle too many more times, there's a 50-50 chance after the 34th mission that we were going to have a disaster, and sure enough, we did. So the question becomes, what could engineers have done about it, or should engineers have done differently? Should we have allowed politicians to keep the project going, even though we knew the system was not designed to be reliable out to that state? Should citizens and workers have been listening to engineers rather than politicians? In hindsight, we know that the wrong decisions were made. But what's the foresight for the next time? We had the foresight after Challenger to know we shouldn't continue flying, but that's exactly what we did, and we had the very disaster that everyone predicted.